This lecture is on chapter 5.1 through 5.2, which is going to be our introduction to the gas laws, which I like teaching because it's something that we can all normally relate to. I think we have some idea what's the relationship between temperature and volume, pressure and volume, and temperature and pressure. And so those are the three gas laws we're going to learn about today: Gay-Lussac's law, Charles' law, and Boyle's law. And then once we're done looking at each of those relationships, we're going to combine them all into the combined gas law. Okay, let's warm up a little bit of review. We're asked to assign oxidation numbers to each atom in calcium perchlorate. Okay, here is the formula of calcium perchlorate, and this is an ionic compound, and so the calcium ion exists as the +2 ion, and hence there's its oxidation number, +2. The participants in the perchlorate ion, well, they all have a total oxidation of -1. Remember, when you have an ionic compound, meaning a polyatomic ion, that the sum of the oxidation numbers is equal to the charge on that polyatomic ion. Okay, so our chlorine charges plus 4 oxygen charges is equal to the -1. We're going to assign the expected oxidation number to that oxygen, since it's the most electronegative, and then clean it up. The chlorine minus 8 is equal to 1. Let's add 8 to both sides to get that the chlorine is +7. So again, the calcium was +2. It's a +2 ion. Charge of an ion is its oxidation number. Chlorine is +7, we just determined, and oxygen is -2. We're asked to assign oxidation numbers to each atom in sulfuric acid. I hope you remember how to come up with a formula of sulfuric acid. We begin by asking, what's the formula of the sulfate ion? And that's sulfur with 4 oxygens and a -2 charge. And so the parent acid, instead of having the -2 charge, has 2 hydrogens. That's where it got the -2 from stealing the electrons from the 2 hydrogens. Okay, and the sum of these three elements' oxidation numbers is equal to 0. We're going to assign the expected oxidation number to the least and most electronegative element. So that's a +1 to the hydrogen and a -2 to the oxygen. And then we'll let the guy in the middle, the sulfur, essentially balance it out. Let's go ahead and distribute these and then clean it up. So the sulfur minus 6 is equal to 0. So the sulfur must be +6. Or +1 for the hydrogen, +6 for the sulfur, and the -2 for oxygen, which we nearly always see for oxygen. So again, for hydrogen expect +1, for oxygen expect -2. And now, what is the oxidation half reaction for the reaction of zinc with hydrochloric acid? Okay, the oxidation half reaction is for the species losing electrons, and that would be the zinc. So there's a zinc losing electrons to form the zinc ion. Then, to balance the half reaction, we begin by balancing the element being oxidized or reduced. I see one on the left and one on the right, so that's already balanced. Then we add electrons in order to balance the oxidation number, and zinc goes from a 0 oxidation number to a +2, and hence it lost 2 electrons, so 2 electrons show up on the right. Step 2C is to add hydrogen ions or hydroxide ions in order to balance the charge, but do note we have a 0 charge on the left and a 0 charge on the right, so it's already charge balanced, so no step 2C, and since there's no oxygens involved on either side, there's no step 2D either, where we would have added water in order to balance the oxygen. Normally we do have a step 2C and step 2D. This is one of the few examples where we didn't. Okay, what is the oxidation half reaction? Oh, same question, only we're going to do it the short way, where step 2A, we balance the element being oxidized, and that's zinc. Do note I give myself a lot more room to put things in. And then step 2A, balance the element being oxidized or reduced. One zinc on the left, one on the right. Step 2B, balance the oxidation number, and zinc goes from 0 to +2. telling us that it loses 2 electrons. I think we can see that anyway. To form a +2 ion, it lost 2 electrons. Step 2C is to add hydrogen ions in an acid to balance the charge, or to add hydroxides in a base to balance a charge. But this was already charge balanced, so there was no step 2C, and there's no oxygen, so no step 2D. And now, what is the reduction half reaction for the equation below? Well, let's see which species, which element is being reduced. Well, the iron's going from +2 to +3. It's losing electrons, so it's being oxidized. What about that manganese? Well, what's the oxidation order of manganese in the permanganate ion? Well, what +4 times -2 is equal to -1? Or what -8 is -1, and that's +7. On the right is +2, so the manganese gained electrons, so that's the element undergoing reduction. Since we're going to do this for both an acid and a base, I'm going to write it twice because it'll be different for each. Okay, on to step 2A, balance the element being reduced. 1 manganese on the left, 1 on the right, so that's already done. Step 2B, we add electrons in order to balance the oxidation number, and we already saw that manganese went from a +7 to a +2. And that means how many electrons and on which side? Well, it's gaining 5 electrons, so +5 electrons on the left. Then step 2C, to balance the charge, well, let's see, in an acid we're adding hydrogen ions, and I see 6 negatives on the left, 2 positives on the right. So it looks like we're going to have to add 8 positives to the left. In a base, we have 6 negatives on the left and 2 positives on the right, so we're adding 8 negatives to the right. And now time for step 2D, adding waters in order to balance the oxygen. I see 4 oxygens on the left, in the acid reaction, 4 oxygens on the left and none on the right, so I need 4 waters on the right. In a base, 4 on the left and 8 on the right, I need 4 more on the left. And note, it also balances the hydrogens without us even needing to worry about it. Now we're asked to write a balance equation for the following in acidic solution. Well, the manganese in permanganate is still +7, and manganese 2 is +2, so we see that's our reduced species. But what's the oxidation number of nitrogen in the nitrite ion? Well, what +2 times -2 is equal to -1? +3 minus 4 is equal to -1, so the nitrogen's in a +3 state in nitrite. What about in nitrate? Well, what -6 is -1? +5. Okay, so the nitrogen is undergoing oxidation, and the manganese is undergoing reduction. Okay, now step 2B, we're going to balance these, and so 1 nitrogen on the left, 1 nitrogen on the right, that's already balanced. Then 1 manganese on the left, 1 manganese on the right, that's balanced as well. Then step 2B, we add electrons to balance the oxidation number, and the nitrogen went from +3 to +5, which means it lost 2 electrons. The manganese, on the other hand, went from +7 to +2 by gaining 5 electrons. Now, step 2C, we add hydrogen ions to balance the charge. I have 1 negative on the left, 3 negatives on the right. I'm going to add 2 positives to the right so that it balances the left. Now I have -1 balancing -1. For the reduction half reaction, I have 6 negatives on the left, 2 positives on the right. Since I'm adding positives, I need to add 8 positives to the left. Step 2D, our final step in balancing the half reaction, is to add water to balance the oxygen. For the oxidation half reaction, I need 1 more oxygen on the left And in the reduction half reaction, I need 4 oxygens on the right. Okay, now that we've completed step 2, balancing the half reactions, step 3 is to add these 2 half reactions together so that the electrons cancel. Since I have 2 electrons on the right and 5 on the left, the least common multiple is 10, so I'm multiplying equation 1 by 5 and equation 2 by 2. And that gives us 5 nitrites, 5 waters, 2 permangates, 16 hydrogens on the left, 5 nitrates, 10 hydrogens, 2 manganese 2s, and 8 waters on the right. And note we have waters and hydrogens common to both sides, so we're going to reduce both sides by the smaller number. So it'll be the 5 waters. That gets rid of waters from the left. And the 10 hydrogen ions, which gets rid of the hydrogen ions from the right. And there's our final balanced equation. Okay, write a balanced equation for the following reaction in acidic solution. Okay, well, first let's put into our 2 half reactions, and let's see what's going on with that chromium. Well, what's the oxidation number of chromium and the chromate ion? Well, what minus 8 is equal to -2? Remember, I'm saying that because the sum of the chromium's oxidation number and the 4 oxygen oxidation numbers is equal to -2. So my chromium plus 4 -2s is equal to -2. So my chromium minus 8 is equal to -2. What minus 8 is -2? Positive 6. And over on the left we can see it's positive 3. So that was our reduction half reaction. What's the oxidation number of sulfur in the sulfite ion? Well, what minus 6 is -2? Positive 4. What is the oxidation number of sulfur in the sulfate ion? Well, what minus 8 is -2? Positive 6. So the sulfur is undergoing oxidation and the chromium is undergoing reduction. Okay, that was step 1. Step 2 is to balance each half reaction, starting with step 2a, balancing the element being oxidized or reduced. So on the oxidation half reaction, 1 sulfur on the left and on the right. In the reduction half reaction, 1 chromium on the left and on the right. So no real step 2a. Step 2b, we add electrons to balance the oxidation number. And I would remind you that sulfur went from +4 to +6. You might actually want to write that +4 above the sulfur in the sulfite ion and +6 above the sulfur in the sulfate ion. And going from +4 to +6 means we lost 2 electrons, so 2 electrons show up on the right. For the reduction half reaction, well, we already saw that chromium went from +6 to +3. Again, we might write that +6 above chromium and chromate, and the +3 above chromium and the chromium 3 ion. And so, how many electrons are on what side? 3 electrons on the left. Okay, step 2c is to add hydrogen ions in order to balance the charge. And for the oxidation, I have 2 negatives on the left and 4 negatives on the right, so I need to add 2 positives to the right. Now I have -2 balancing -2. And for the reduction half reaction, I have 5 negatives on the left and 3 on the right. I need to add 8 positives to the left, and now I have +3 balancing +3. Time for step 2d, our final step in balancing the half reaction, where we add waters in order to balance the oxygen. And I need 1 more oxygen on the left in the oxidation half reaction, and 4 more oxygens on the right in the reduction half reaction. And now our 2 half reactions are balanced. Again, most of our work goes into step 2. Step 3 is to add the 2 half reactions together so that electrons cancel. Since I have 2 electrons on the right and 3 on the left, the least common multiple is 6, so I multiply equation 1 by 3 and equation 2 by 2. And this time I'm going to recognize that I have 3 waters on the left and 8 on the right, and reduce both sides by 3. And then I have 16 hydrogen ions on the left and 6 on the right, so I reduce both sides by 6. You feel that it's easier doing like we did in the last problem and writing it all out. So we have waters and hydrogen ions on both sides and then reducing them. Nothing at all wrong with that. Okay, on to new material, and in preparation for the gas law equations, let's first talk about the 4 variables that we can identify a gas by. And those 4 variables are the volume of the gas, the temperature of the gas, the pressure of the gas, and the actual amount of gas, which we measure in moles. So these are the 4 variables that define a gas. Now for our first work with the combined gas law, or excuse me, with the gas law equations, we're going to hold the number of moles of gas constant. Okay, now let me talk about temperature, because only one temperature unit will work, and that's absolute temperature, and that'll be kelvins. When it comes to pressure, let me go ahead and define that, and that would be a force per a unit of area. So think of pounds per square inch. Pounds is a force unit, square inch is an area unit. Now, we actually get the pressure of a gas by the constant bombardment of gas molecules with a surface. Now, our pressure units begin with what's called a millimeter of mercury. Now, I'm sure there's been a time when you have put your finger over a straw and pulled some soda out of your drink by simply holding your finger over the straw. Then you let loose with the straw and the liquid came out. We have the same principle here with the original barometer, where we used a tube full of mercury because it's much more dense than water. If we use water, this would be about 30 feet high, so that's why we chose mercury, so it's only about 3 feet high. And essentially we tipped it over and some of the mercury came out, but if we were at sea level, 760 millimeters of mercury would have stayed in that tube. Now do note, it doesn't matter how long that tube was, only 760 millimeters of mercury would remain in it. Now, of course, if we go to different altitudes, we'll have different pressures, and so that height will go up or down. Okay, another unit of pressure is the torr, which is actually just another name for millimeters of mercury, so same thing. 760 millimeters of mercury would be 760 torr. And that's what's known as the standard atmosphere, or the atmosphere, and this is essentially the average pressure at sea level. Now keep in mind that pressures change based on not just your altitude but on weather, and so we've defined 1 atmosphere as 760 torr, and of course that's the same as 760 millimeters of mercury. So you do need to know these relationships so that we can convert between these 3 pressure units. When it comes to volume, doesn't matter what volume unit you use, and for moles, well, there's really only 1 mole unit. Okay, on to those gas laws. And the first gas law we're going to talk about is Boyle's law, and Boyle talks about, and his law relates, the relationship between pressure and volume. Now, think about a piston, maybe a syringe, and you pull that piston out while the one end is closed. Essentially, you're pulling out the piston, you're increasing the volume. But what's happening to the pressure inside that piston? Is it going up by you pulling out the piston, or is it going down? It's going down. And so what we see is that pressure and volume have an inverse proportionality. As pressure goes up, volume goes down. As volume goes up, pressure goes down. And you can think about taking that cylinder or that syringe and pushing it in. Then you're decreasing the volume and increasing the pressure. So we can write this inverse proportionality as the volume is proportional to 1 over the pressure. That squiggly refers to proportional to. Now as an equation, we can write that as the volume is equal to a constant divided by the pressure. And we can rearrange that equation so that we have the pressure times the volume is equal to a constant. And that constant would depend on what the temperature was and how many gas molecules you have, but at the same temperature and the same number of gas molecules, it would be constant. So you could change your pressure and it would change your volume, and you could change your volume, and of course that would change your pressure, but the product of those two will be equal to the same constant. So that gives us that P1 times V1 is equal to that constant, so that's your initial pressure and volume. And this is also equal to your new pressure and volume, so we'll call that P2 and V2. If you want to use I's and F's for initial and finals, that works quite as well, but I use 1 for initials and 2's for finals. And I think you know where we're going with this, is they both equal the constant K, then they both equal each other, and that's Boyle's law. P1 times V1 is equal to P2 times V2. Hence, if I know my initial pressure and volume, and I know my final pressure or volume, I can calculate the other one. Let's do an example. We're told a gas in a flexible container means that the volume can change, occupies 125 milliliters at 22 degrees C and 1 atmosphere of pressure. If the temperature is constant, find the volume when the pressure is 0.75 atmospheres. Okay, well, the pressure is changing, and we want to see what happens to the volume. So we bring out Boyle's law. P2 times V2 is equal to P1 times V1. I just put the 2's on the left because we're after the 2. We're after the new volume V2. So here I've solved for V2. And V2 is equal to V1 times P1 over P2. Now those pressures are both in the same unit of atmospheres. So I can go ahead and plug them in. If one was in atmospheres and one was in millimeters of mercury, I'd have to convert one into the other. Do note here, the atmosphere units cancel, leaving us with the appropriate units of milliliters. Okay, our volume went up. Does that make sense? Well, our pressure went down, so yes, it does make sense. The next equation is for Charles' law, and Charles defines the relationship between temperature and volume, and I'm pretty sure that we're familiar with this. I'm sure there's been a time when we've left a soda bottle on our dashboard in the summer, and when we came back, that bottle was all bloated as it gained volume inside the bottle. So that tells us that as temperature goes up, the volume goes up, and hence these are directly proportional. As you increase one, you increase the other. Actually, as you would double one, you would double the other. And we can write this proportionality as the volume is proportional to the temperature. And we might rewrite that as the volume over the temperature. Okay, I'm here ahead of myself, so essentially the volume is equal to a constant times the temperature, which we could rewrite as the volume over the temperature is equal to a constant. And we're going to do the same thing we did in the last problem. That's why we want to set this equal to a constant so that we can then say if our initial volume over our initial temperature is equal to that constant, and our final volume and our final temperature, our volume over our final temperature is equal to that same constant, then those two would be equal to each other, and there's Charles' law. V1 over T1 is equal to V2 over T2. I would point out we could derive these in a pinch if we forget these equations. The last one, let's do an example, and then we'll go over the last law, Gay-Lussac's law. And in this example, we have a sample in a flexible container with 425 milliliters of volume at 25 degrees C and 1 atmosphere. If the pressure is constant, now do note, to have Charles' law be applicable, the pressure has to be constant. Okay, find the volume when the temperature is 98 degrees C. Okay, well, we're looking at two different volumes, two different temperatures. So there's Charles' law. V2 over T2 is equal to V1 over T1. I just put the 2's on the left because the 2's to me represent what we're after, the final. And I'm after the new volume, so I'm going to multiply out T2, and here's my V2 isolated. I do have each of these variables, and do note that your temperatures have to be in kelvins. I don't think you'll ever find that in this class. We'll be using temperatures in degrees C. Expect that your temperature will always need to be in kelvins, but especially for gas law problems. And again, do note that the temperature units of kelvins cancel to give us the appropriate unit of milliliters. And when I asked, does my final answer make sense? Well, I had an increase in volume, and that was due to an increase in temperature. So yes, that does make sense. Our last equation, and I'm going to refer to these as changing gas equations, because essentially we had the same gas and we just changed its condition, and hence we didn't have to talk about the amount of gas. Okay, this last is Gay-Lussac's law, and this is the relationship between temperature and pressure. So what is the relationship between temperature and pressure? Are they directly proportional? Does one go up as the other one goes up? Or are they inversely proportional, where one goes up as the other goes down? Well, I think we know if we increase the temperature of a gas, it's going to increase the internal pressure if we don't change the volume. And so they are directly proportional. And so we can write this as the pressure is directly proportional to the temperature. And as an equation, we can write this as the pressure is equal to a constant times the temperature. We can set one side equal to a constant and say the pressure over the temperature is equal to that constant. I think you know where we're going with this. So our initial pressure over our initial temperature is equal to that constant. And later on, our new pressure over our new temperature is still equal to that constant. And that gives us the Gay-Lussac equation. P1 over T1 is equal to P2 over T2. And so now we can relate temperature and pressure together if the volume is held constant. Let's do an example. A gas sample in a rigid container. Rigid means the volume isn't changing. Flexible means that it could change. Rigid is not. At 25 degrees C has a pressure of 1 atmosphere. If the temperature is raised to 98 degrees C, what is the new pressure? Okay, the relationship between temperature and pressure, P2 over T2 is equal to P1 over T1. And we're after the new pressure, P2, so we're going to multiply out T2. And as in any gas problem, we have to change from any given temperature that's in degrees C into kelvins. At 25 degrees C is 298 kelvins. At 98 degrees C is 371 kelvins. And note how the two Kelvin temperature units cancel to leave us with the appropriate unit of atmospheres. Does our answer make sense? Our pressure went up due to our temperature going up. Yes, that sure does make sense. Okay, now we want to combine all of these three equations into one equation. That way we can relate temperature, pressure, and volume and change two and see what happens to the third. So we don't have to hold one of those constant. Now we can derive these based on what we've already seen. Let's look at those three gas laws. P over T was equal to a constant. P times V is equal to a constant. And V over T is equal to a constant. Now note how in each of these, the pressure and the volume are on the top, and the temperature is on the bottom. So when we try to put these all into one relationship, we're going to have P and V on the top and a T on the bottom. And now this is equal to a new constant. And now this new constant only depends on one thing, and that's the amount of gas that you actually have. So we can change 2 and have the third one change as well, so all 3 of them can be changing at this point. Okay, and I think you know where we're going with this. If our initial pressure times volume over temperature equals this constant, and our final pressure times volume over temperature equals this constant, and that gives us our combined gas law equation. P1 times V1 over T1 is equal to P2 times V2 over T2. Keep in mind the P's and V's are on the top, the T's are on the bottom of both sides. One side has the 1, one side has the 2's. And again, this means that for a changing gas, which means that we have the same gas, same number of molecules of gas, we can change 2 of these variables and calculate the third. In other words, all 3 of these variables can change at once. Okay, let's do an example. A gas in a flexible container occupies 1 liter at 0 degrees C and 480 torr. Find the volume when the temperature is 100 degrees C and the pressure is 0.562 atmospheres. Okay, well, first, we're using an equation for this, so we might break out that equation, or we can go through and identify what those variables are, but I think I'm going to just start with the equation, and that is P2 times V2 over T2, remember P's, V's on the top, T's on the bottom, is equal to P1 times V1 over T1. And we're after what? The new volume, so let's divide out the P2 over T2, which means we're multiplying by the inverse, T2 over P2. And now here's our equation isolated for the variable we're after. Now back to the data, and do note our temperatures need to be converted into kelvins, and we have one pressure in torr and one pressure in atmospheres, so we need to convert one into the other. Let's actually do that first with our units, and so step 1, we're after atmospheres, starting with step 2 at 480 torr. We could just as well start it with the 0.562 atmospheres and convert it into torr if we wished. And now step 3, out of torr and into atmospheres, and I hope you remember how many torr per atmosphere? 760 torr per 1 atmosphere, and this is a number that you eventually need to remember. Putting this on my calculator, I come up with 0.632 atmospheres. For my temperatures, I'm adding 273 to each of these, and so for T1, 0 plus 273 is 273 kelvins, and T2, 100 degrees C plus 273 is 373 kelvins. And note how all units cancel but the one we're after. Now what if we had made the mistake and put our units in torr in there? Well, if we want to cancel them, we would see that they don't cancel. So our units are there still to help us make sure we're not making some simple mistakes like overlooking that we had 2 different units for our pressure. And I come up with 1.54 liters. Does our answer make sense? Well, we had an increase in volume, which would match a increase in temperature. And it would also match a decrease in pressure. So I have lots of confidence that my answer is correct. I hope you're getting in the habit of asking when you're done with the calculation, does my answer make sense? Okay, there is an alternative method of solving these changing gas law problems, and it's a variant on unit analyses. And I think you'll find it's pretty simple. Now, step 1, we have to get our units from somewhere. So if we're after V2, then it gets its units from V1. If we're after T2, it gets its units from T1. P2 would get its units, of course, from P1. So there's step 1. Your final unit comes from your initial unit. Then step 2, well, the other factors affecting the system have to cancel. And so the other factors would be pressure and temperature, and so they cancel. I put a P over a P and a T over a T. This should be pretty much a no-brainer, doing step 1 and step 2. Step 3 is where we have to stop and think about this. And this is where we need to determine Well, which P is that on the top? Is that my new pressure or the old pressure? Which temperature is that on the top? Is that T2 or is that T1? Now, to determine this, we simply would ask, if I increase this unit, does it increase the one I'm after? In other words, if I increase pressure, does it increase volume? No. If I say no, that means the new guy, the 2 goes on the bottom. If I say yes, then the new guy goes on the top. Because if I say no, then they're inversely proportional, so the new guy goes on the bottom. If I say yes, then they're directly proportional, and the new guy goes on the top. Let's do an example. A gas in a flexible container occupies 1 liter at 25 degrees C and 521 torr. Find the pressure when the temperature is 95 degrees C and the volume is 0.572 liters. Okay, well, we're using our units for this, and so P2 must get its units from somewhere. P2 gets its units from P1. Then, what are the other factors affecting this system? And of course, that would be the volume and the temperature. So I put V over V and T over T. And step 1 and step 2, pretty easy. Now comes step 3, where we have to think about this. If I increase my volume, do I increase my pressure? No. Think about that syringe pulling out the plunger. You decrease the pressure, so that means that the new guy goes on the bottom. Again, if the answer is no, then they're inversely proportional, and the new guy goes on the bottom. What about temperature? If I increase my temperature, does that increase my pressure? Yes, increasing temperature increases pressure, so they're directly proportional, and that means that the new guy, the 2, goes on the top. And do note, not only did this give us our equation, but it's already isolated for the variable that we're after. Okay, let's see, we needed to convert those temperatures into kelvins. Plugging this all in. Do note, my volume units of liters and my temperature units of kelvins cancel, giving me confidence that I've done this correctly, as it gives me the appropriate unit of torr. Okay, does our answer make sense? Well, we have an increase in pressure. Does that make sense? Well, we had an increase in temperature, and we had a decrease in volume. Both of those would cause an increase in pressure. So yes, our answer does make sense. Okay, let's practice some of the things that we learned here today. We're told a gas sample in a flexible container occupies 1.25 liters at 122 degrees C and 0.831 atmospheres. If the temperature is constant, find the pressure when the volume is 1.71 liters. Now, let me point out that our combined gas law equation handles Charles' law, Boyle's law, and Gay-Lussac's law all at the same time, and so we really only need one equation, our combined gas law equation. P2 times V2 over T2 equals P1 times V1 over T1. Now, if you have an instance like this one where the temperature is constant, then those two variables cancel out, meaning the temperature units cancel. And that then gives us the pressure-volume relationship, Boyle's law. So again, we didn't need to separately remember Boyle's law because it came right out of the combined gas law equation. Okay, and we're asked after the new pressure, so P2, so we divide out V2, and here's P2 isolated. And let's see, the pressure unit, okay, our volume units are the same, and our pressure unit is atmospheres. When we cancel those liters, we're left with that appropriate unit of atmospheres. We do need to always look and see, do we need to convert some temperatures or some pressures? But in this case, we didn't. Does our answer make sense? A decrease in pressure due to an increase in volume? Yep, that makes sense. Okay, next, a gas sample in a flexible container occupies 725 milliliters at 250 degrees C and 1 atmosphere. If the pressure is constant, find the volume when the temperature is 22 degrees C. Well, we're still going to start with our combined gas law. because we only need one equation. We don't need all four. We just need this one. P2 times B2 over T2 equals P1 times B1 over T1. And anybody held constant? Yes, the pressure is constant, so we can just remove them from the equation, giving us V2 over T2 is equal to V1 over T1. Essentially, that's Charles' law. And now we're after the new volume, V2. So let's multiply out T2, and here's V2 isolated. Do we have these three variables? Yes, we do. And our temperatures, as they normally need to be converted from degrees C into kelvins. At 22 degrees C becomes 295 kelvins. At 250 degrees C becomes 523 kelvins. Note how kelvins cancel, giving us the appropriate units of milliliters. And we had a decrease in volume. Does that match a decrease in temperature? It certainly does. So we can have confidence in our answer. Now, are we 100% sure this is correct? No, we're just sure that it's not grossly incorrect. Okay, a gas sample in a rigid 2.50 liter container at 425 degrees C has a pressure of 10 atmospheres. If the temperature is reduced to 85 degrees C, what is the new pressure? Okay, we're using our combined gas law problem, using our combined gas law equation. And so P2 times V2 over T2 is equal to P1 times V1 over T1. And let's see, anybody held constant? No, not this time. And we're after the new pressure. So we get P2 by itself by dividing out V2 over T2, which of course means we're multiplying by the inverse. Oh, we weren't given a new volume, so that actually did cancel. And that gives us Gay-Lussac's law. Okay, and now find a new pressure. So we multiply out T2. And we have these three variables. Again, temperatures need to be converted into kelvins first. At 425 degrees C becomes 698 kelvins. At 85 degrees C becomes 358 kelvins. And we're simply adding 273 to our temperature in degrees C to get our temperature in kelvins. And I come up with a much reduced pressure. Does that match our data? Yes, we have a much reduced temperature, so that does match our data. And again, that rigid told us that the volume was going to be constant. A rigid container. Volume is not changing. Okay, let's see. In one of these, I'm going to use the unit approach. A gas in a flexible container occupies 1 liter at 0 degrees C and 712 torr. Find the pressure when the temperature is 1150 degrees C and the volume is 1.13 liters. I'm going to use my combined gas law equation again. And I'm after, well, actually, let me double check and be more careful this time. Is there anybody that's held constant? No, both changed. And so we're after the new pressure, P2, so we divide out V2 over T2 by multiplying by the inverse, T2 over V2. And there's our equation isolated for P2. And let's see, we need to convert those temperatures into kelvins. Everybody else can go in as is. And this time we had a greatly increased temperature. A slightly increased volume. So I'm predicting an increased pressure. And sure enough, there's a greatly increased pressure, 3,280 torr. And I would remind you that at any time you want to practice this on your own, just stop the video and do it on your own, and then you can see me doing it with you. Okay, gas and flexible container occupies 128 liters at 225 degrees C and 921 torr. Find the volume when the temperature is 22 degrees C and the pressure is 572 torr. I think this time I'm going to use my units. And so V2 must get its units from somewhere. They get it from V1. And what other factors affect this system? Temperature and pressure. So I put a T over a T and a P over a P. And now, if I increase my pressure, does that increase my volume? No. So the new guy goes in the bottom. If I increase my temperature, do I increase my volume? Yes. So the new guy goes on the top. And now, are my pressure units in the same unit? Yes, and my temperature units need to be converted into kelvins. And I get just a slight volume change. Does that seem to make sense? Well, my pressure went down, but so did my temperature. So yes, it does make sense, because my pressure going down would mean an increase in volume, but my temperature going down would mean a decrease in volume. Okay, a gas in a flexible container occupies 625 milliliters at 25 degrees C and 0.912 atmospheres. Find the temperature when the volume is 125 milliliters and the pressure is 5.72 atmospheres. Okay, I think we're going to use our units again, and so we're after the new temperature, so T2 must get its units from somewhere. It gets it from T1. And the other factors affecting the system are volume and pressure. And now I ask, if I increase my pressure, does that increase my temperature? And I have to say, that doesn't really work for me. I don't think of temperature as being dependent on pressure, but I do see it the other way, so let me just ask it the other way. If I increase temperature, does that increase pressure? And the answer is yes, telling me they're directly proportional, so the new guy goes on the top. And if you're saying yes, the new guy goes on the top. And now volume. If I increase volume, does that increase temperature? And again, I have a hard time with that, so I ask it the other way. If I increase my temperature, does it increase my volume? Oh, yes, it does. They're directly proportional, so the new guy goes on the top. Again, if your answer is no, they don't, no, it doesn't increase, then it's inversely proportional, and the new guy goes to the bottom. If the answer is yes, it does increase, then it's directly proportional, and the new guy goes to the top. Okay, there's my equation already isolated for the variable I'm after, and both my pressures are in the same units. My temperature does still need to be converted into kelvins, as always. And my final temperature, 374 kelvins, or 101 degrees C. Now do note I had a decrease in volume and an increase in pressure. The decrease in volume would match a decrease in temperature, but the increase in pressure matches an increase in temperature. So that's why it really didn't change a whole lot. I mean, it did change some, but not a tremendous amount. Again, we should always be looking and trying to figure out, does our answer make sense? Because if we've made a mistake, we want to catch it. Okay, that concludes this lecture where we covered the gas laws, and we were introduced to first the measurements on gases, volume, temperature, pressure, and the number of gas molecules. And then we're introduced to the gas laws, Boyle's law, Charles' law, and Gay-Lussac's law, which we ended up combining all into one equation. So we really only need to remember one equation, the combined gas law. P1 times V1 over T1 is equal to P2 times V2 over T2. Just remember P and T on P and V on the top, T on the bottom. And it doesn't matter which side gets the ones and which side gets the twos, as long as one side gets the ones and the other side gets the twos. Okay, that concludes this lecture.